Hi everyone, this is our 12th lecture. We're going to be talking about nonlinear relationships today. I actually really like this lecture because it shows how flexible regression can be. It takes it beyond even interactions, which shows a lot of the flexibility, but this shows that linear relationships don't always have to be present in order for us to use linear regression. So when we talk about nonlinear, we're talking about when the relationship between a predictor and the outcome isn't represented very well by a straight line. And right here, this is an example of a quadratic effect. So this is where it starts a little bit higher, goes down to some minimum and goes up. Or you could see something very similar where it starts low, goes high, reaches a high point and comes down. Those are quadratic effects. Here's the quadratic effect again on this side where we have the x plus x squared. That's what a quadratic effect is. It's just a square of our variable. And then on this other side we have the square root. So that would be looking at the relationship between the square root of x and how that affects y. Both are forms of nonlinear relationships. Having nonlinear relationships gives us some opportunities to ask some new questions, questions that we couldn't ask without a nonlinear relationship happening. For example, we can ask what value of x produces the lowest value of y, or highest. So we can say where is it at its min? So what value of x produces the lowest value of y, or the highest if it looked different than this one. It also can answer questions like, where does the effect of x wear off? Where is it the largest? These are really important questions, especially as you get into situations like dosage effects. If you're looking at an intervention and you want to be able to say, it's about this much that you need in order for it to really give you the benefit. But anything more than that doesn't really help a whole lot more, so it flattens out. Or in some cases, you're going to see that too much of something is actually going to have problematic effects, so it's going to go back down. We'll see a bunch of examples today, but the idea is that we can ask a lot of very specific questions when we have a nonlinear relationship. It makes it more complicated, but it also allows us to ask more complex questions. So one question is, how do we know if there's a nonlinear effect? Because we've talked about in this class that there really isn't any relationships that are probably exactly linear. But we've said that a line often represents a relationship pretty well. So what do we mean by nonlinear? Well, in simple regression, to find it, we really want to look at a scatter plot. We should be looking at this early on anyway. We always want to see, does the relationship look like a regression could explain it well? Well, maybe our relationship kind of looks like that. And so if we look at the scatter plot, we could know it looks like there might be a nonlinear relationship here. However, in multiple regression, the residual scatter plot can be very informative, because the regular scatter plot can hide nonlinearities, but it still can be really difficult to see graphically. A lot of nonlinear relationships are subtle. They're not super strong. That makes it so it can be very difficult to see. So I always suggest checking using the graphical methods first, looking at residual plots. But you also can test it. And I recommend doing this anytime that you think that there could be a nonlinear relationship, or if a nonlinear relationship would be important or is tied to your research question. For example, if we're talking about dosage effects, we don't want to give too much of anything. So it's an important part of our question is to say, where does this level off? How much is enough? Because we don't want to do anything beyond that. Our question may also have to do with where's the maximum value that we get. So what value of our predictor would give us the best outcome? So if our research question is reliant on the nonlinear relationship, then we need to test it. So I wouldn't just test no matter what. I would test if your research question has to do with it, or if there's good reason to think that there's a nonlinear relationship. Definitely test those, but I wouldn't just test it every time. Now, when I'm saying test it, there's two general approaches at looking at nonlinear relationships. They're the two most common. There's a lot of other approaches as well. We'll refer to a few of those towards the end of this. But the first one's polynomial regression. It basically is with a quadratic effect or more. We'll talk about that in a moment. And then spline regression. And that one's where you basically split up the regression into different pieces. So you'd have one piece that's a straight line for this part, and then another piece that would be a straight line for that part. And then we'll see towards the end that you actually can combine these in some ways. So when it comes to polynomial regression, all we're doing is including what we term higher order variables. Higher order is just where you have a higher number on the power. So x squared is a second order variable of x, so that's a higher order of x. X cubed is a third order variable of x, and you could keep going up. And each one is just a higher order. So one thing that's interesting is if you notice that the lower order of x squared is included in that model at the top. Why would we want to include the lower order of x? So one of the reasons why is whenever we leave a variable out of a model, we are basically saying that its coefficient must be 0. If we have it out of the model, the coefficient must be 0 or must not matter for our situation. So if we leave out a lower order of a variable, so we have x squared in there, so we also include x. We include x because we want the model to be able to fit the data the best. And in order to do that, we have to include x so that it can give a value for its coefficient that's not 0. That's one of the reasons. The other reason is if we don't include it, then we're constraining how we can interpret the model. We're constraining what it can do. If we include it, then we're not constraining it. We're allowing it to be flexible and fit the data and give us the full gambit of results. So anytime you have an x squared in there, you're generally going to want to have an x in there. If you have an x cubed in there, you're going to want to have an x squared and an x in there. So we always want the lower order of whatever your highest order is in the model as well. Now, to interpret the polynomial regression, it does require a little bit of calculus. And I know that can be totally scary. That's fine. I know a lot of you haven't taken calculus in a long time or ever. So I'm just going to show you a few shortcuts on how to use it so that you can interpret these variables without having to go through a lot of effort of learning calculus. So let's say this is our model and we got these results. So we have 2 is our intercept, 1 is a coefficient on x, and 2 is a coefficient on x squared. To take the derivative, which is a calculus thing, what we need to do is find all the places where we have x1. This is very similar to what we did in interactions. So we're going to find all the places where there's x1. And in this case, we have that here with the 1x1, and then we also have it in the 2x2. And what we're going to do with those variables, if it's just a regular x1, there's no power to it, you're just going to drop that variable. So we're just left with 1 for that part. And then where you have a squared variable, you're going to take the 2 and put it in front of the x, and then the x is just going to stay. And so you're going to have plus 2 times 2 x, not squared anymore, just x. So we took the 2, we put it in front of the x, and then we just took away one of the powers there. So we had 2 and now we only have 1. So x to the 1 is just x. So what we have is the effect of x1 is 1 plus 4 times x1. So I'll say that one more time. To take the derivative, we're going to find all the places where we see x1. If it's just x1 on its own, we're going to just take the x1 away and leave the coefficient, whatever the coefficient is. So in this case, 1. And then we're going to do plus, and then we had a 2 for the coefficient, so we keep that one. And then we bring the 2 from the power of 2, the x squared, that 2, we're going to bring that down. So we now have 2 times x. And we take away one of the powers. We had 2, now we just have 1. So we're left with, again, the effect of x1 is equal to 1 plus 4 times x1. So getting away from the calculus, if we just accept that the calculus worked and this is the result, that our effect of x1 is 1 plus 4 times x1, the effect is really similar to what we had with an interaction. But instead of being dependent on another variable, now the effect is dependent on its own value. And I'll show what this means in just a moment. But the idea is that depending on where you are on x1, the effect of x1 is going to be different. So consider this plot. So here, depending on where we're at, the effect of x1 or the effect of what changes in y when we move x by 1 unit depends on where you're at on x1. So for example, if we are at x equals 1, we're starting there and we increase x by 1 unit, then the effect of x is positive right there. If we're at x equals 1, the effect of x is positive. But what's the effect of x when x is negative 2? It's actually a negative 1. If we look at where negative 2 is on that plot and we go 1 unit, that is saying depending on where we are on x, what our value is, that depends on what the effect of x is going to be. If we are below 0, in this case, this is just one example, if we're below 0, then the effect of x is either negative or flat. And if we're above 0, then it's flat or positive. That's just this example right here. So again, the effect of x1 depends on the value of x1. That's the idea. When you have a polynomial, that is how you interpret your predictor. With this information, once we have found the effect of x1, we actually can find the min or max point. In this case, it's the min because there's a bottom, not a top to this shape. So the way that we're going to find the min in this case, we're going to set the effect of x equal to 0. Because that is actually the definition of the min or max. It's where the effect of x becomes 0. So if you think about this, if we're on this side, the effect is negative. At some point, it has to turn positive. But right at that point before it turns positive, it has to be 0. If we're going smoothly from negative to positive, at some point, there's a point where it's 0. That is the minimum point. So if we set the effect of x equal to 0, when the effect of x is 0, so for a 1 unit increase in x, it just is flat on y. And then we solve for x, that's going to give us our min. So in this case, if we set it to 0, so 0 equals 1 plus 4 times x1. If we use some algebra, so we minus the 1 over, and then we divide by 4, we get the min point is negative 1/4. So when x1 is negative 1/4, that is the minimum point in this graph. So if you look at that graph, right before it gets to 0, that is the minimum point of this relationship. So it's at that very point where if you're more negative than negative 1/4, x has a negative effect. If you're more positive than negative 1/4, then x has a positive effect. And right at that point, that is the minimum. We'll see a few more examples. So if it's not making sense yet, just stay with me. So when it actually comes to using the polynomial regression, we want to use centered variables. We want to center any variable that will have a higher order in it. So if we're going to use x squared, we want to center x at its mean. This just makes it so the variance inflation factor stays lower. It's just kind of a nice trick that we can use. And then you just include higher orders based on visualizations, theory, or hypothesis tests. I generally recommend the two. So if you have seen that this looks like there's a nonlinear relationship, or according to theory, or your research questions are asking for it, then definitely include those. And then run the regression just like any other that we've run before, and you're going to look and see, is there a significant quadratic effect? Now note, nonlinear relations can sometimes be hard to find even visually. And sometimes you may even need to look at the outcome / predictor with the covariate controlled for or removed. So when you're in multiple regression, one of the difficult things is there could be a nonlinear relationship that shows up once you've controlled for certain variables. So after I control for certain things, maybe that's when a nonlinear relationship shows up. So for example, this might be what the relationship looks like without controlling for anything. But once we control for stuff, it looks more like this, which has a slight curve to it. My point of saying this is that this is a complicated situation. You're probably going to miss some polynomial relationships. And honestly, that's going to happen. It'd be best if that didn't, but it's just the fact of life. These are very difficult to find unless theory or your research question or something visual makes you think that there is a relationship there, and so I should test it. Now note, while you're thinking about that, you may think, well, I'll just test every polynomial relationship and I won't miss any. The issue with that is that the polynomial regression is known to overfit to the data. So it could fit to the noise in the data. It might think that something that's just noise is something important and it latches onto that. So we don't want to overuse polynomial regression because it has a tendency to find situations that really aren't quadratic or a polynomial in any way. So you don't want to overtest. You always want it to be based on your research questions or theory or visualizations of the data. And now spline regression. This is a fun one because basically what it does is it chops up your data into little bite-sized pieces and fits a linear model to each piece. So it's just like having mini regression models for different sections of your X variable, your predictor. Now the cutoff points can be decided based on visualizations, theory, or you can have an algorithm make that decision. If the section is not significant, then that can be removed from the model, that section. So the way that we actually do this in practice is we need to define all the joints, all the places where the relationship switches. So you might have one point where the relationship looks like this, and then the next after that it flattens out. So this point where that switches would be one of the joints. We're going to call those J variables. Now we include all the J variables in the model once we've created those, and we run the regression just as we've done before. So consider if we want to set a joint at x equals 2, Then x is the same. We don't change anything about x. But then j becomes x minus 2 when x is greater than 2. Otherwise, it's 0. So x is still the same predictor it was before, but now j is basically your x variable. But now we're doing x minus whatever the joint number is, so 2 in this case, when x is greater than 2. The rest of the time, j is 0. So any points where x originally was below 2, j is just going to show up at 0 there. And then we just run the model, y predicted by x plus j. You can always let the algorithm decide the best fit. That's fine. Sometimes that can overfit, sometimes it's great. And there's some ways that we can do that, and we'll show a few in the in-class examples. But I want you to consider this situation, this example. So in this case, we have both polynomial and spline shown, and a smooth spline, which we'll talk about in a moment. And we have just a regular linear regression shown. What we have here is the hours of exercise per day and its relationship with overall health. Now, this is totally fictitious data, but theoretically, I think we could argue that if someone's exercising a good amount of hours, it's helping their health up to a point. Then at some point, if they're exercising more than that, it's actually probably hurting their health in some way. And so the relationship that you can see in the data has a slight curve to it where it starts low, reaches a max somewhere around 6 to 7 hours of exercise per day, and then starts to decrease after that. So this top one, top left, we just have a line fit to it. And what you can tell is the line doesn't quite represent the data very well. A lot of points are below the line on the lower end and on the upper end. But in the middle, there's not very many points below the line. All of them are above, basically. That's a good hint that this line is not quite representing this data super well. So that's our linear relationship, probably not our best one. And then the next one over is the polynomial with just a quadratic effect in there. This one fits the data pretty well, where you see it is saying that in a few hours, if you're exercising a few hours and you increase how much you exercise, it's going to benefit your health. But then somewhere around 7 hours-ish looks like the peak, maybe 7.5. At that point, increasing your exercise isn't going to help you. It's actually going to start hurting your health. So that's what our polynomial is saying right there. And we could get the coefficients out and we could find the exact effect of hours of exercise per day on overall health. And then we have the spline. And the spline is very similar to the polynomial, but instead of a smooth curve, now you just have a sharp corner. And this sharp corner looks like it's somewhere around 6 hours of exercise per day. At that point, so before that point, when you exercise less than 6 hours per day, it says the effect of increasing your hours of exercise will just benefit your health. So if we're working out at 2.5 hours and we decide, I'm going to increase my hours of exercise, then we would predict that it would help that individual's health. However, if you're past that cut point, so you're past that 6.5 where it is that sharp cut, then we'd say anything beyond there, if you're increasing your exercise, it's actually going to hurt you. The best thing you could do at that point is actually decrease your hours of exercise. And then this last one, the smooth spline, is essentially a combination of spline and the polynomial, where you're still splitting it up into these pieces that the spline does, but now instead of just a sharp corner, it smooths those over with a really nice quadratic effect. So all of these, except for the linear, would suggest that as you increase the amount of exercise you do, it benefits your health up to a point. And that point is somewhere between 6, 6.5, 7, 7.5, somewhere in there, where if you're beyond that much, if you increase your exercise, it's going to hurt your health. Not by a ton, but it looks like it's going to hurt your health. Now, we don't get that kind of interpretation if we just assume that's a linear relationship. We just assume that it always, if you increase your exercise, it's always going to benefit your health. And in this case, that doesn't represent the data very well. So we interpreted these. Note that they're not as straightforward to interpret. They're more complicated. But they also provide more in-depth information. In situations like this, I think it's totally worth the complexity to try to describe what it means in order to get the relationship right. To say, up to a certain point, increasing your exercise is going to do you a lot of good. But after that point, then it's just going to hurt you. That's an important concept to make instead of just saying if you increase your exercise, no matter how much you exercise, it's going to help. And so that's the core of the polynomial and spline regressions. We'll show several examples in the in-class activities to show you actually how to do them. But in general, that is the idea, that they allow us to use a nonlinear relationship and get a lot of information out of it. I think both spline and polynomial are highly useful in situations where you think there's a nonlinear relationship. There are sometimes, though, that the polynomial or the spline aren't going to be quite right for your situation. There's another approach that we can take, and it's using what are called monotonic transformations. These basically are just transforming the outcome or the predictors or both to make the relationship more linear. So we just change the variable with some transformation. This in turn makes it so the relationship may be more linear, and so we don't need to use a spline or a polynomial. Now, some common monotonic transformations include logarithmic, or the natural log is what we're going to use a lot. Or there's another one called box-cox. We'll introduce this briefly in the in-class activity. When we talk about logarithmic, there's three basic forms of this. You have log-lin, log-log, and lin-log. What those stand for is if it's on, so log-lin stands for we're transforming our outcome with a log transformation, but the predictors are still just linear. Log-log says we're transforming the outcome and the predictor with a log transformation. And then lin-log is saying that the outcome is linear, but the predictors are log transformed. Depending on what you pick is going to influence how well the assumptions are met, how well a line fits the data, and how you interpret it. Now with box-cox, that uses different powers of the predictor. So you don't have to just use square, cubed. You can use square root. You can use a power of a third. You can use a power 2.2. Box-cox is actually a test to find the optimal power to make the data linear. And we'll show that in the in-class example. Now note, monotonic just means that the transformation doesn't change the order of the data points. It changes how closely spaced they are to each other, but it does not change the order. So if I am below you on some measure, using a monotonic transformation means I'm still below you, but it changes the distance between us. It changes how below you I am. Now, because log transformations are really common, I want to just highlight a few things about the log transformation itself. First, when we say a log transformation in stats, we almost always mean the natural log, which is normally rho ln. We're just going to write log. They're interchangeable here. We're not going to ever mean another type of log in this class. The estimate also, which is really cool, mathematically approximates to the percent change in the outcome when the outcome is log transformed. So for example, if we did this where y is the log transformation but x is just linear, which if you remember is log ln, that's a log ln model, that 0.03 means for a 1 unit change in x, there is an associated 3% change in y. I think this is really cool. So you can still, it's really interpretable even when you use a log. In the in-class example, we'll show a few other examples of this so that you can see how to interpret log and ln log as well. But in general, this is the idea. For some change in x, there's an associated percent change in your outcome. Now for this one, there's just one additional resource. This is a good one talking about nonlinear regression. It's talking about polynomial and spline models. Take a look. These can be, the resources that I share at the end of each lecture can be really helpful, especially if you have some questions about it, or sometimes they're also very applied and can show you how to do it in R. Please take a look at it and let me know if you have any questions. And then, because this is on YouTube, in the comments below, feel free to say if you know what movie this is from. Or in the discussion post, say what movie these two things are from. It's one of my all-time favorites. I'm not going to tell you in this video, but tell me if you know what it is. And we'll end with that. Thank you.